in-depth review. So here we have our main function. At the start of our function, we create a Boolean variable named loop and we set it to true. We then enter a while loop where we initialize a pipeline object named tester. This object has its own constructor, which then proceeds to run its own set of functions and programs. At the end of that program, we return to main and we input a string response. If response is y, loop stays true, and so the while loop continues again, creating a new pipeline object which runs once again its own functions. However, if the response is anything but y, loop becomes false and we break out of the while loop. Finally, we return 0 to signify the end of our main function. Oh, and also if you have time, check out this YouTube video. It's very informative.
When a pipeline object is created, we set our PC to 0 and our instruction count to 0, and then run select file. Inside of select file, the user is prompted to enter a program for execution. If their entry matches one of our files, Fibonacci, factorial, test, or life, those names, or the file names, then that specific file will be read by read_CSV. If they enter exit, then the program will terminate. If their entry does not match exit or one of the files, then an exception is thrown, an error is printed to the screen, and the user is prompted to select another file.
So here we have our read_CSV function. This function is used to read an inputted CSV file and write to the CSV contents vector in memory. At the start of the read_CSV file, we create a string type variable named temp element, which will hold all the elements, as well as a vector of type unsigned integer called values. We create an if stream called myFile, which reads from the file. We then open myFile, and if myFile is open, we enter a while loop, where we continue to look at myFile as long as we haven't reached the end of the file. Inside of this while loop, we use the getLine function to grab the very first element up until the comma. We then take this element and we write it into an unsigned int variable named temp, and we have to convert it from a string to an unsigned long. From there, we push temp into our values vector using pushback. Once we do reach the end of our file from the while loop, we exit it and we close myFile. Once we get out of this if statement, we want to make sure that values, the vector, isn't empty, and if it is, we want to throw the exception empty. However, if everything is good to go, we want to write to the member variable CSV contents, which is inside the memory class, using this values vector we have inside of read_CSV.
Once select file has ran, we go ahead and call our run for the PC of 0. Inside of run, we have a while loop which checks if our PC is less than our content size, so we don't try to run an instruction through the pipeline that doesn't actually have an instruction. As well, it checks if the reorder buffer is not empty. In the while loop, we first go and fetch the instruction at that PC number. Inside of fetch, we go and check that there is space within the fetch width to continue in our for loop, and again reconfirm that we're not trying to fetch an instruction that doesn't exist. At the end of each for loop, we increment I and we increment total calls, and total calls is used for outer latency. Next, we check that there is space in the IQ and the reorder buffer to add more instructions. Once inside all of that, we call uint to binary for the instruction. Let's go look at uint to binary. The uint to binary function converts an unsigned integer to a binary string. To do this, we use a bit set of 32 because we want a 32-bit binary string. Given is the instruction passed, and then we use the to_string to convert it all to binary. This is saved in the binary underscore string, which is a member variable in the instruction class.
So the decode function is used to determine what type of instruction format, either R, I, J, or P type, each element in the vector string from the instruction class actually is. From there, it also writes to the destination bits, SRC1 bits, SRC2 bits, and anything that's related to those parameters. So let's get into it. At the very start of the function itself, we create a string named typebits, which checks the very first two characters of the binary code string using the substring function. Once we collect that, we go into a couple of if statements that check what type the actual two characters are. If it's a 00, that means that our instruction format is an R type. So we write to the opcode bits, des bits, SRC1 bits, SRC2 bits. We also need to determine what the opcode is from the binary code that we collected here. We'll use the decode opcode function for this, but we will explain that after this entire function. We also need to write to the member variables inside of the instruction class, and namely in the R type, we write to dest, SRC1, and SRC2. Because this is an R type, we don't collect an immediate, so we're going to set that to -1 for now. Moving on, for the I type, we need to check if the type bits are 0, 1. We do a very similar process as before, where we write to the opcode bits, des bits, SRC1 bits, but this time we write to the immediate bits rather than SRC2. We again use the decode opcode to check whether it's addition or multiplication, subtraction, or so forth. From there, we once again write to the member variables of the instruction class, but this time we write to dest and SRC1 and immediate only. Moving on, if the type bits are 1, 0, that means we're a type J. Because this is a jump case, we only have to collect the address bits of where we're jumping to. So we only have to write to address. And finally, if the type bits are 11, this is a P type. So again, we collect the opcode bits and des bits, and once again, decode the opcode. We then write to dest inside of the instruction class. So after all that, we enter a while loop here, where basically we want to check that the parameter that the user enters is not greater than 31. We also check if it is less than 0, and we also check, finally, if it is equal to 0. All of these cases would normally break our program, but because we made this exception class, we shouldn't have problems if they decide to enter these numbers. And that is the end of the decode function. Okay, so now let's take a look at that decode opcode function that we mentioned earlier. It's a rather simple function, and all it does is it checks what the string parameter that was passed and how it was laid out. If it was all zeros, it was an add type. If it was all zeros with a 1 at the front, it was a subtract type, and so forth. At the very end, we also make sure to check whether the opcode might have been invalid for whatever reason.
Inside fetch unit, we have our JType, BEQ, and BNE functions. In our JType function, we set the PC for the next instruction to fetch to the value of the address in our current JType instruction. For our BNE, we test if the source 1 and the destination data are not equal. If they are not equal, fetch is redirected to fetch the PC at the value that is equal to the immediate value of the BNE instruction. If they are equal, then we continue on just to the next PC number. For BNE, the opposite happens. If the source 1 and the destination data are equal, then we redirect the PC and fetch to the value of the immediate in our current BEQ instruction. And if they are not equal, then we continue on like normal. Take a look at our setRB element and our setIQ element functions. Our setRB element is the exact same for all of the different types of instructions. We use the RB element constructor with 3 parameters. Our first one of 0 will set the validity to 0. The second one we are passing the binary string to, and our third one we are passing our PC number to. In our set IQ element, we indeed test for the different types, R, I, and P. We don't test for J because a J type will never make it into fetch, and we don't want to put it onto the IQ. We just want to divert the program. For R type, we set our opcode, source 1 validity from the register file, source 2 validity from the register file. We set our source 2 to -1. Our destination, PC number, and type, those all come from our instruction class. For the I type, it is roughly the same. However, our source 2 will be saved to -1 so that we don't use the information and set to valid. And our immediate will be put in instead of a source 2 from our instructions. For the P type, we take the opcode. All of our destination and sources are set to -1 and 1 because we are not using those sections of the instruction, and we pass our immediate.
So here we have the register file function, which is used to construct a register file object. At the start of this function, we resize the R vector inside of our register file.h header to the size of 15, which is set to register size. We then go into a for loop where we go through each element in the R vector and set its data to 0 as well as its validity to 0 so that all of them are valid. And that is that function. For the execute function, we use it to check if the instructions in the IQ are ready for execution, and if they are, we continue with the execution. So at the very start, we set up a iterator right here that starts at the beginning of the queue. We will enter an if statement as long as it has not reached the end of the queue. Inside the if statement, we have our debug statements here, and we output the relative parameters that we are looking for inside of the statement here. We then enter a for loop where we set I to 0 and we increment as long as I is less than the issue width and the size is not equal to 0 for the queue. Inside the for loop, we have another debug statement that checks the status of src1 and src2 to see whether they are 1 or 0. Outside of the debug statement, inside this if statement, we check to see if the destination IQ is 0, because this would mean that we are trying to write to register 0, which is impossible. We're not allowed to write there. If that is the case, we throw this exception here. Otherwise, we move forward. Here we have another debug statement that outputs the instruction that is ready to execute, as well as the operation that we're going to use. We enter another if statement here that basically checks what type the IQ is at that place. If it's an R type, we first want to check if it's a print statement. If it's a print statement, we enter this area here where we simply see out the final results. In a special case where the answer is 42, we want to output that it's the meaning of life. So moving on, if we are trying to write to the destination IQ that is 2, we want to throw another exception because R2 is not a register that we are allowed to write to. If we are trying to write there, we throw this exception right here. While we are still in the R type loop, we want to check what the operation code is to do the necessary operations. For example, if the opcode is add, we want to write to the register of the destination, and we want to set it to be equal to the src1 register plus the src2 register's data. And we do that for add, subtract, multiply, divide, modulo, and move is slightly different. For move, we simply set the destination IQ register to be equal to the src1 register. Outside of that, if the type IQ is I and not R, we first have to try to see if we're once again writing to R2. If we're trying to write to R2, it is not allowed, so we throw this exception. Otherwise, a very similar series of steps to the R statements above are followed. We write to the register of the destination IQ to be the src1's register's data plus the immediate value that is passed to it. We can do the add, subtract, multiply, divide, and modulo operations. Finally, if the type IQ is a p-type, which is a prompt type, we simply write to the destination IQ register to be what the immediate IQ value is. Moving on, we have another debug statement here that will output the executed. And we also want to set the validity in the register file at destination IQ to valid to signify that it has been executed. We then enter this for loop here, which basically sets the ROB in the ROB ID file at destination IQ to valid to signify that it has also been executed. We have another debug statement here, which outputs the ROB ID IQ as marked. Finally, we want to pop the front if all has been successful. Otherwise, if the SRC1 was not valid or the SRC2 was not valid, we want to output an error as we are not ready to be executed. Regardless, we want to increment our total calls and total instructions executed by 1, and we want to also increment our total execute calls by 1.
When we get to commit, we enter into our for loop. With each iteration of the for loop, we check if there is still space in our commit width and that our ROB is not empty and there are still instructions to be committed. When we first get in, we increment our total calls, which is used in our statistics, and then we check if the front of our ROB is valid. If it is valid, we will pop off the front of the ROB and increment total commits. If it isn't valid when we're in debug mode, we will see out an error that we could not commit, and then we leave the commit function.
When we finish fetching, executing, and committing in the run function, we enter the statistics portion of our lab. So we can first look at our print statistics function right here, which is going to be used for calculating our latency and calculating our throughput. For calculating latency, we simply want to divide the total amount of calls by the total amount of commits that were successful, and that gets us our latency. For calculating the throughput, we want to calculate the total instructions that were executed and divide it by the amount of times that we called execute. And that gets us throughput. Here at the end, we also include another execute statement where we see out the average latency per instruction as well as the average throughput per instruction. Makefile.
Inside our makefile, at the very top for our output, we list all of the different classes as well as our main file as .os. And then below, we create all of our .o files from the dependencies for main for .cpp, and all the classes, we have both the .cpp and the .h, and then it has the compilation for the .cpp beneath it. At the very end of our makefile, we also include a clean so that we can clean our make and recompile everything from the beginning. Sometimes when we are switching between our execute and debug mode, our makefile does not seem to recompile edited files, and it is sometimes necessary to do make.clean and then make again to recompile everything.
Execute mode. Okay, here we're going to demo our execute and debug phases. So for the first bit, we're just going to have execute run and not our debug. So to begin, we're just going to do a make clean just to wipe the previous makefile, and then we're going to make it again. And once all of that has outputted, we're just going to type output. And then we can choose a program here. So let's start off with Fibonacci. So we're going to enter the first parameter here. So let's enter something like 5. And as we can see, our final result is 5. We have our average latency here, and our average throughput shows up as well. We were then asked if we'd like to test another program. So let's type in y for yes. And let's try factorial this time. Let's enter the parameter 5, so we should get something like 120. And we do. So it also outputs our latency again and throughput, so all of it is good. Finally, let's try out test. And here, again, final result is 2. For our program, which we've named life, we've opted to take in user input and basically work our way to reduce the input down to 1. Once we reach 1, we're going to multiply by 6, followed by 7, and get the output of 42, which is the meaning of life. So as we can see, if we type in life and throw in something like 7, the meaning of life is 42. And that concludes the execute portion of this. Debug mode.
Shouts to all my lost boys. Shouts to all my lost boys. We rowdy. Shouts to all my lost boys. Shouts to all my lost boys. We rowdy. Shouts to all my lost boys. Shouts to all my lost boys. We rowdy. Shouts to all my lost boys. Shouts to all my lost boys. On your ready, bass. On your ready.
Nice. Stop it. Get some help.
Now we're going to check out the debug program rather than the execute one. So at the top here, we're just going to uncomment out define debug and comment out define execute. We're going to save it, and like before, we're going to make clean again to wipe the previous makes and make it again. And once that completes, we're going to do ./output, and we're going to select our first program. So let's do Fibonacci. And let's make our parameter 6. So the output becomes a huge list of fetches, instructions, and executes. So at the very top, we take in 3 PCs because our fetch width is set to 3 currently. We then set all of them into the instruction queue and execute. So 3 of them go into execute because our execute width is 3. And because our commit width is 3, we're also going to commit 3 of them at a time. In the following fetch, we reach a BNE, which ends up stalling our pipeline. Here, only 1 enters the instruction queue, and therefore only 1 is executed and only 1 is committed. In the following fetch, we take 3 PCs, however, 1, again, is set in the instruction queue, and it is also committed. Moving on, it continues, and here we have 3 being fetched, 3 being executed, and 3 being committed. And it continues until we reach the very end of the program, which outputs... Okay, and we continue until we reach the end of the program, and because we have execute undefined currently, we won't output our answer. If we want to select a new program, we're going to type in yes, and we're going to select factorial. Let's do the same parameter that we picked last time, which was 5. So, like Fibonacci, we spit out all of our fetch, instruction queues, executes, and commits. There's a lot of scrolling, sorry. And like before, we're just going to follow the pipeline. So we fetch the first 3, then we execute all 3 of them and commit all 3 of them as well. And then in the following fetch, we once again fetch in 3 of them, execute 3 of them, and commit 3 of them. And here we have another BNE statement where PC6 causes us to revert back to PC3. So like before, we take less instructions in and execute less things because of the BNE, and that also leads us to commit less things. And this program will also continue until the very end, where once again our print statement doesn't show. If we enter the test file, once again we get a very similar output. Finally, if we try out our life file and enter a parameter of 6, we get a very similar output. And that concludes this demo. So for the first graph, we looked at the latency where all of the parameters were set to 7 for each different CSV file. In every case, however, the widths were changing. So the dark blue, the widths are all 2. For orange, the fetch is set to 2 and the issue width is set to 5. For the gray, the fetch is set to 5, but the issue width is set to 2. For the yellows, the latency has all widths set to 3. And finally, for the light blue one, all of the widths are set to 5. So, as we can see, latency never increased regardless of the widths. It only depended on the parameter. So, as we can see from this, latency never increased regardless of the widths. And we're going to follow up on that with this graph here. So in this case, the latency changes with various parameters when we set the fetch, issue, and commit width all to 3. So in this case, again, with the dark blue, the parameter is going to be 2. With orange, the parameter is 6. With gray, the parameter is 13. With yellow, it's 22. And finally, for light blue, it's 30. So when the widths are kept constant and we change the parameters, we can see that the latency does actually change. The inst.mem CSV file does not take a parameter, thus the latency is constant here. Fibonacci CSV and our meaning of life CSV have a relatively constant latency, only changing a tenth if at all, and that's the case right here, where we do change, we increase a bit, but only by 0.01. This is likely due to the fact that the BNE does not occur that many times. Fibonacci has a very high latency for parameter 2, as if 1 or 2 are entered, the program automatically returns 1. For factorial CSV, as you increase the parameter, the latency increases. However, the higher the parameter, the smaller the change between consecutive parameters. As we can see, this.
As you can see, the higher the width, the better the throughput. For the width, the smallest width between fetch and issue dictates the maximum throughput, and the commit width has no effect. As you can see in that dark blue bar, when the throughput, all of the widths are 2. We're at 1.5 for our instant instruction memory. And then we go to our red bar where our fetch width is 2 and our issue width is 5 and our commit width is 2. It is the same as our blue bar because our fetch, which is before our issue width, is still 2. When you go and have your fetch width as 5 and your issue width and commit width as 2, some of the programs we stay the same because in the end we still only have 2 going out. And in our Fibonacci and our test program, it increases slightly. And then when we go to yellow and all of our widths are 3, all of the graphs accordingly increase. And again, when all of the widths are 5, we increase again. The best performance occurs when the widths are large for our throughput and the parameters in our program are small, as shown from our latency graph.